Otrashchenko, Otrashchenko, Zakhar, Akimov, Nikolay, Efanov. Okay, please. Please.
So, hello everyone. I'm Alexey Otrashchenko. My co-partner is Zakhar Akimov, and we would like to present you our work, development of optimization framework for embedded software based on automatic tuning of GCC compilers optimization phases. So. Our presentation will be as follows. We'll have a little introduction. We'll overview our framework. Then we'll discuss two approaches we took, the genetic algorithm and the reinforcement learning. We'll discuss our results and compare them and to make a conclusion. So basically, nowadays, there is a rising demand for performance and efficiency of programs, and modern compilers partially help with optimizing performance, power consumption, and reducing the binary sizes with their optimization phases in their intermediate representation. But one note, the optimization phases are applied in strict order, and there were articles that show that reordering this sequence of optimization phases can significantly improve your program's performance. So compiler auto-tuning problem arises. Basically, the main platform for compiler auto-tuning is LLVM because of convenient LLVM IR, which has a lot of tools to work with it and a lot of methods of characterization. But on the contrary, embedded system usually use GCC as their toolchain. So there was no way to auto-tune compilers via phase reordering for embedded systems. Thus, we state our problem as following. We want to develop a framework and a method to reorder phases in a GCC compiler, and we want to integrate our developed framework into existing solutions for compiler auto-tuning, with our target being size reduction of size of binary without performance loss. We did this on function granularity and on whole program granularity.
So compared to LLVM, GCC does not provide method of path reordering, and we had to implement it ourselves. There were two approaches that can be taken: patching the source code of the compiler and using its plugin API. We chose the second approach as it allows us to integrate our solution with already existing workflows and compilers without needing to recompile them. Unfortunately, as GCC does not natively provide path reordering, passes have some implicit dependencies that, if not followed, will cause the compiler to break and provide incorrect binary that will not work correctly. So with the plugin, we have developed a path sequence validator that we will call a shuffler module that checks for internal GCC dependencies and external dependencies that we have figured out experimentally. Furthermore, the plugin allows us for getting the embedding of the function by passing its intermediate representation, and using and all of this validator plugin and characterization processing script were integrated in a compile regime environment that provides a simple API such as take a step, apply a pass, look at the new embedding, and get a reward from improved and size runtime. This environment will be later used in reinforcement learning.
So let's discuss our first approach with genetic algorithm. Let's do a quick recap of what is a genetic algorithm. We have a population of individuals that are characterized by their objective function. We start with some initial population that might be seeded or might not in place of interest. So for each individual, the objective function is calculated,